Now that we have introduced the definite integral, let's look at when a function is integrable and how we can understand the integral as area. First, we talk about integrability. A function is integrable if the limit exists. Now, the important theorem. If a function is continuous on the closed interval from a to b, then it is integrable on that interval. So in simple terms, if the graph has no breaks, no jumps, no holes, then we are guaranteed that the definite integral works. Now let's move to the main idea, definite integral as area. You can see in this graph, some parts of the curve are above the x-axis and some parts are below the x-axis. This is really important because the integrals don't just measure area, they measure something called signed area. Let's start with the first case. If the function is above the x-axis, meaning f of x is greater than or equal to 0, then the definite integral of f of x is the area under the curve. Look at this part of the function is above the x-axis. So this shaded region is the area under the curve. And the area is positive. So this is just the normal area you are used to. Now look at the part of the graph below the x-axis. If f of x is less than or equal to 0, then the definite integral of f of x is the negative area. This part of the graph is below the x-axis. This shaded region is the negative area. So even though it has size, the integral subtracts it. So when we combine everything, the area above the x-axis is positive, the area below the x-axis is negative. That's why the integral gives something called the net signed area. Now let's connect this to the definition. We split the graph into two parts, A1 and A2. A1 is the area above the x-axis, and A2 is the area below the x-axis. So if I want to find the definite integral from this point to this point, that is called the net signed area. We take A1 minus A2. So we subtract the part below the x-axis. But sometimes we want the total amount of area, so we use the absolute value. The definite integral of absolute value of f of x equals a1 plus a2. So to find the net area, we take a1 minus a2. To find the total area, we take a1 plus a2. Now, let's look at example 1. We're given the function f of x equals x minus 2 over the interval from 0 to 6. We want to find two things. Part A, the net signed area, and part B, the total area. Let's use the graph on the right to understand what is happening. First, notice that the graph is a straight line. It crosses the x-axis at x equals 2. That means from 0 to 2, the graph is below the x-axis. So this area is negative. From 2 to 6, the graph is above the x-axis, so this area is positive. So I'll call this A1 and this A2. To find the net signed area, I take the area above the x-axis minus the area below the x-axis. To find the total area, I just take the area above the x-axis plus the area below the x-axis. To do that, I need to find this area and also this area. A1 is this area, is a triangle. To find the area of a triangle, I use a formula 1/2 times base times height. This is the base and this is the height. The base equals 2 and the height equals 2. So I have 1/2 times 2 times 2, which is 2. A2 is this area, which is also a triangle. So I still use the formula 1/2 times base times height. This is the base, which is 4. And this is the height, which is also 4. And 1/2 times 4 is 8. To find the net signed area, I take the area above the x-axis, which is A2, minus the area below the x-axis, which is A1. Which is 8 minus 2, which is 6. And this actually represents the definite integral of the function f of x from 0 to 6. To find the total area, I take A1 plus A2, which is 2 plus 8, which is 10. So the total area equals 10. And this represents the definite integral of the absolute value of the function f of x from 0 to 6.